introduction. So, right, let's begin. So what do we mean by resource elastic? Starting, let's give you a rough idea. So in a CPU world, we expect the operating system is going to keep the utilization up to 100%, right? If you have a one task, it will get the full of CPU time. If you have, let's say, two, then it will split the time in between them so that utilization is kept to the maximum. We're trying to do the same thing, but with the FPGAs, right? Why do we want to do this? So FPGAs are being deployed at a large scale, right? In industry, with the different vendors providing it in the cloud services. At the same time, academia has, large-scale, exascale products where they're trying to use FPGA as a backbone to break the limit of thinner scaling and Moore's law. Right? And such a large-scale system means if you want to make the most out of the big investment and the infrastructure you're going to do, you want to share them as in multi-systems, as we do, multi-tenants, as we do for the CPU systems. Right? But if you look at the current infrastructure at the node level for FPGAs, what we have is essentially a run-to-completion model. It's like old-school CPU systems, right? Where we don't really do a context switch because it tends to be really expensive. So for FPGAs, we don't only have to pay the partial reconfiguration penalty, but we have to read and write the whole entire state, which in case of FPGAs could all be VRAMs, registers, and everything. And this could be quite considerable, pretty much equivalent to the PI itself. So we don't tend to do a context switch, right? And what does this mean? We cannot move the accelerator around inside FPGA, let alone inside a cluster, right, for load balancing. And in most cases, it tends to be one application per FPGA. And we don't tend to take benefit of the free resources which may have available, right, at the runtime, because the static allocation of reconfigurable resources. We're trying to change that because what happens is, as you see, it's quite easy to land in a spot like this where you have a long range task, but overall your system is quite heavily underutilized at a runtime scenario. So what we're trying to introduce is a concept called resource elasticity to try and fix this. What we define resource elasticity as the ability of a kernel to grow or shrink an accelerator, right? Resource footprint, to be exact, reconfigurable resource footprint at runtime, right? What do we mean, grow or shrink? Well, you can grow and shrink in two different ways, which we consider right now. You can replicate an accelerator, right? So you can grow more resources that way, or you can change the microarchitecture itself, right? Have bigger data buffers, share the control logic, and you can go faster potentially. Replication is potentially going to give you, ideally, linear performance, probably one. Microarchitecture can give you super linear performance because you can have same control logic with bigger data buffers, more data reuse, right? So now such a system, when you start growing, considering idea of growing and shrinking accelerator, comes with its own set of trade-offs, right? Three being the prime one. When do you replicate? When do you switch to different accelerator implementation? Right? That depends on what other kernels are doing and what their workload is as well. Same thing. Do you want to run to completion or do you want to change the module? Because you're going to pay a heavy penalty, right? Even if you don't save the state or restore the state, you're still going to pay the penalty PR. Same thing, and since the spatial domains, right, FPGA, you run into fragmentation issues, right? If you look at that one, how do you fill it up? Do we put another instance of A, or do you want to split the whole thing out, put a different implementation module for each of them? And this, all of them, depends on the runtime scenarios, how much work you have left at that particular point in time, what acceleration benefit your new module is going to get, and so on and so forth. Right. Now, even if we assume such a system exists, right, where you can grow and shrink the thing, you still have to solve the problem of context switching. If we go to the primitive preemptive scheduling, we have to store all of this state at any point in time. So we need the circuitry and ability to save all of the large state which can potentially exist during the execution point. What we propose is rather a cooperative scheduling model, right, where you only do context switching when you have your small state, in order to reduce the amount of time you're going to spend saving and restoring state. That's essentially the most crux of the whole idea, how we work. So in our particular example, right, the experiments we're doing, we use OpenCL as the accelerator to generate the growing and shrinking accelerator we're doing. It's essentially designed for heterogeneous systems. So primary target to be GPUs. So it's built for concurrent networks. The way it works is that it has multiple different lightweight threads called work items, and they're all bundled up together in a work group. So let's say in here you can have J as a work item and I as a work group. Right, and the interesting bit, since it was designed for heterogeneous architecture for GPUs in mind, they don't allow synchronization between work groups, right? So they can be executed in parallel on different cores at full speed throttle. But that also means they don't have an internal state which you need to pass between these cores, right? And that's the main point we exploit for this thing. Is that's the way we do our consistency point, where we do the context switching between them, right? Where essentially our context switching penalty becomes just a PR. You don't have to stir and restore anything because everything is written back to the main memory at the end of work group. So what we have is a system like this, which is, let's see, UltraScale Plus, with 4 partial regions, where we can place our accelerator in any 4 of them, or we can combine them to create a bigger accelerator in. We can also relocate these modules up. And the way these accelerators are generated from OpenCL description using Vivado HLS. The RTL is then pumped through Vivado and our own tools so that we can place it out in the constraints. We can have a relocatable module. Right. Overall, the OpenCL stack, the interface, is kind of the same as we expected in the standard SDXL and the heterogeneous part, where we have our host code running on the ARM core in this case because we use the Zinc platform, and a runtime resource manager which is going to execute things on our compute substrate, right? And the kernel, which user provides, then it's compiled and runtime executes it. The interesting bit from the normal flow is the loop here, where we use user optimization. So what do I mean user optimization? Well, in the HLS you can have pragmas in it, right? You can tell it how much to pipeline, how much to unroll, and so on and so forth. Each of these pragmas with different parameters gives you different microarchitecture, right? Logically, they produce the same thing, but they're going to have different characteristics at the runtime and different area requirements. And that's how we generate our different implementations for the kernels. And the runtime resource manager then basically coordinates which one to put, how much to replicate for them at the runtime, without user having to interpret or anything. Internally, what the runtime is essentially doing is that it's looking at different possible combinations you can have, right? You can have replication of this by 2 slots, let's say, another has a bigger module instead, because it's a critical section, for example. And then you look at all the different combinations, we essentially brute force at the moment, and then you rank them, whatever criteria you're looking for, right? You look for energy or fairness or performance, with the overheads in mind, right? So whatever partial reconfiguration penalty you're going to pay, and then based on that, if, let's say, the performance benefit is better than what we have, right, then we make the changes using the drivers and the PR reconfiguration. And the important bit is this, right? It's not normal time domain scheduling as you would expect. It's cooperative scheduling. So what happens is it schedules only at the end of work group or whenever a new kernel arrives, right? So it only schedules whenever something changes in the system. So overall, the stack which we kind of change is essentially the hardware static system which we play with, and correspondingly the drivers so that we can have program whatever we place in them. And the main bit is the runtime system, which takes into account multiple different applications and allocation and resource management for them. Right? And the interesting bit is we can handle multiple different applications of this, right? And that's what we designed the system for multi-tenancy. So ideally, if you can grow and shrink at the end of work group, right, what you would expect is, let's say if you have A, it's a long-running kernel, and you have some task like B, C, and D, which are short tasks, which are just coming around in your data center, for example. You want to have A, the full size, all of the resources you have available for your task A as an empty FPGA. And then when something comes, you want to shrink it back to something which is decent enough, right? And then something comes, you again shrink, and then when something leaves, you go back to the full scale. This is kind of the behavior which we expect, let's say, in a CPU system, where if you have multiple cores, we split our workload across different cores. In case here, we consider PR regions instead, right? So in terms of evaluation, so that we consider 3 different as a baseline functions, right? You're going to have a run to completion model, which is generally the common thing, or you can use the same context switching mechanisms, right? That is work group. At the end of work group, you switch accelerator, put something else instead. There are two ways to do this. Right? You can always use the smallest accelerator so that you leave most of the space for the incoming accelerator, or you be greedy and go with the biggest bulldozer to get the most performance out of the system. Right? And we compared it with the two different versions of our resource elastic scheduler. Right? They don't have much difference, but they only change the ranking function, which I showed you in the previous slide. One is trying to optimize for fairness plus utilization. The other one is trying to optimize for performance. Now, they're fairly primitive in a sense right now. They don't really look at the feature. They look at one instance and they decide, okay, which is better allocation at this point in time. Alright, let's start with the simulation result. We started with like 1,000 different scheduling scenarios, and you have the results for that. So what we see is kind of performance is logarithmic with the more number of slots you give. And there's not much difference between the PRES and the FRES. Because at the end of the day, both of them are still optimizing for utilizations, which kind of leads to improvements in the performance itself. And the wait time, if you look, they're kind of similar to what you would expect, the cooperative scheduling and the progressive cooperative scheduling. The peaks you see, right, the 4 slots, they're essentially kind of a byproduct of the experiments that we had, where we set the maximum accelerator size to 4 slots in order to investigate what would happen if we have bigger FPGAs, right? But your accelerator is not actually able to fill up the whole chip, or how is the performance going to be in that case? Can it keep up the utilization and performance up? And as a result, what happens is these are the scenarios where an accelerator takes whole FPGA, and then you have to wait for a long while for the PR to happen. And you get peaks. Right, if you look at the overhead, since we brute force into the all possible allocations you can have at any point in time, at any scheduled awakening cost, you see essentially quite a lot of writes, like 10 to 12 to 100 times more overhead in that terms. But this is still in microseconds. Right? Well, partial reconfiguration is going to be in milliseconds. And alternatively, you can have different heuristics to bring it down later in the future, rather than having a complete brute force when it becomes a bottleneck. If you look at the partial reconfiguration costs, right, the moment we introduce the concept of context switching in the system, they're doing much more swapping of the system. So that happens even with the normal cooperative scheduling and algorithms. It goes considerably high. And there's not much of a difference between, let's say, the aggressive cooperative scheduling and this growing and shrinking we are talking about. So, overall utilization of the algorithms, if you look at it, go pretty much full scale, almost. In the baseline, you will have aggressive going pretty much higher all the time because it's trying to keep the FPGA full with the biggest accelerator. But the dips you see, they're mostly the cases where an application doesn't provide an accelerator to fill in the defragmentation holes, which I talked about earlier, or where the ranking function decide, okay, that fragmentation is fine, I accept this trade-off with fairness or performance with the utilization, and then you see a little bit of dip there. Overall, despite all the overheads which I showed earlier, right, and the performance, we still get between 39 to 64% benefit, despite the PR reconfiguration penalties we are paying per context switch. So the case study, so this is kind of the static system we have, which we play with. This is still a big beast of a problem in itself, how to make it. Koa is going to decide to talk about it in the Zilkal workshop, FSP workshop, the first session. What we have for the case study in this paper, what we have is matrix multiplication as a long-running kernel with 2 different implementations, while Euclidean distance and CRC are the short-running kernels which come down and interrupts, let's say, matrix multiplication during execution. So what we get in this scenario is 4 different cases, like conservative cooperative scheduling and normal scheduling run to completion. They're pretty much the same because we have a lot of space to accommodate a new kernel in. Aggressive cooperative scheduling, what happens is it interrupts, but matrix multiplication has the full FPGA, so it has to wait until it finishes, it reaches the end of work group. And then it gets swapped to waiting queue, and we put in the new kernels which are arrived, and then we switch back to the big matrix multiplication. We kind of do the same thing with the resource elastic. Well, what we're trying to do is fill up the empty space we see here with the different instances. trying to keep the utilization up to make the most of the resources. In this case, the difference between the SRAS and PRAS is mostly because PRAS tries to be greedy. It accelerates the biggest workload kernel first and chooses to accelerate matrix multiplication over CRC. SRAS tries to be fair with an equal split and ends up with the right thing, while the other one ends up with the pitfall. So overall performance results, what we get is the wait time is considerably similar with across all of them except the normal scheduling, which is run to completion. But the make span differs considerably for these systems, right? We're talking about 36% if we consider the SRAS with aggressive cooperative scheduling model. And we're currently in the process to do a much more extensive one with the accelerators from the Spectre benchmark. It's kind of running right now. So overall, in summary, what we talked about is business elasticity's concepts and cooperative scheduling, and presented a system which can take accelerator from its HLS description of OpenCL and run it all the way to a hardware static system with considerable performance gains. And the main key takeaways, right, is we need to consider the spatial domain of the FPGAs in the future. With all the shells and different static systems which people are coming up, they need to consider when they do resource management that you take into account the spatial domain to keep the utilization up and not just time domain. And we need to consider cooperative scheduling can actually be a good fit, right? Not doing the swapping of kernels can actually give you lots of underutilization, but if you do it too often, like a preemptive scheduling, right, with a full control when can you do it can lead to lots of penalties in terms of overhead. So cooperative scheduling is actually an attractive idea for FPGAs. Overall, well, resource elasticity, you can have other different benefits like keeping the performance high, utilization. You can migrate the kernels actually accelerated inside the FPGA or across the FPGA because now you can stop it, right? And you can do overall commitment of resources. You can swap it back to the waiting queue and put it back whenever you need to, as long as you're not, of course, violating the quality of services. The interesting bit is the user doesn't actually have to take care of keeping the whole FPGA up. The runtime system can take the responsibility and dynamically replicate them for the user. Nice.
Thank the speaker.